So case 3 is where we have a row of all zeros. Case 4, as it describes in the text, tells us that the Routh array will actually tell us a lie. It'll indicate that the system is stable, marginally stable, when the system is actually unstable. So I want to do an example with case 4 so we can see how we would identify case 4 as different from case 3. So I'm starting with this characteristic equation. S to the fifth plus s to the fourth plus 4s cubed plus 4s squared plus 4s plus 4. I actually invented this characteristic equation by multiplying a bunch of polynomials together, and I made it such that I knew I was going to come up with case 4. So you can do this yourself too, if you prefer. So the s to the fifth row, by inspection, is 1, 4, 4, and the s to the fourth row, again, is 1, 4, 4. So let's go ahead and build the row. We create our alternate universe over here. Let's go ahead and build the row for S3. So S3 starts with an element of 0 because the coefficient B1 is built by 4 minus 4 over 1, so that equals to 0. The element for B2, again, 4 minus 4 over 1 equals 0. And then the third element of the B's is 0 by inspection. So let's go ahead and substitute the values epsilon here. So for S2, we see that C1 equals 4e minus e, 4 epsilon minus epsilon over 3, or 3 epsilon over 3, which reduces to 3. The second element in the S squared matrix is 4 epsilon minus 0 divided by epsilon equal to 4. So let's go on to S1 now. D1 is equal to 3 epsilon minus 4 epsilon over 3, or minus epsilon over 3. And then by inspection, 0 for the second element of S1. For S0, we can multiply minus epsilon over 3 times 4, minus 0 divided by minus epsilon over 3. So that's going to reduce to just be equal to 4. So we take the limit as e approaches 0. We get a minus 0 and a 0. So this tells us that we have 4 poles on the j omega axis. Is this right? Let's check. So we're going to use synthetic division here to confirm that if we build an auxiliary equation based on s to the fourth, which is the row above our first row of all zeros, that this is going to tell us that this delta 1 of s is actually a root of the system. So s to the fourth plus 4s squared plus 4 into s to the fifth plus s to the fourth plus 4s cubed plus 4s squared plus 4s plus 4. So first multiplying by s, subtracting away, then multiplying by 1, s plus 1, we get a 0 value remainder. So we know now that the roots of our system are s to the fourth plus 4s squared plus 4 times s plus 1. So you can actually see, if you're good at factoring, that this turns out to be s squared plus 2 squared times s plus 1. So we do in fact have 4 roots on j omega. So let's rewrite this again. 4 roots on j omega. Is this stable? Well, the answer is no. Another question might be, is it marginally stable? So first of all, let's review. Why isn't a system with roots on the j omega axis stable? Well, here we mean that it's actually stable, that for any input that's bounded, you'll get a bounded output. So we'll see here why even marginal systems that are marginally stable, are not stable. But first of all, this system is definitely not stable. Let's check now to see whether it's marginally stable. If you take the Laplace transform of some function, for example 2ks over s squared plus k squared squared, you can see that I've borrowed the denominator here from this term, s squared plus 2 squared. So if we assume that k is the square root of 2, because this is the characteristic equation, we don't know exactly what's on top. So I've just assumed that it's, for example, some 2ks over s squared plus k squared squared. So in a standard differential equations book, you can look up this inverse Laplace transform. It turns out to be t times sine of kt. So this, unfortunately, is not a bounded result. So as t gets bigger, then it seems that our value is going to increase with t. So even though sine is bounded between -1 and 1, we're multiplying by t. So that's no good. But it may actually be that even though this is our characteristic equation, we have something else on top, right? So what if it's not 2ks on top? What if it's s squared minus k squared over s squared plus k squared squared? So this is another form of something that has the same looking characteristic equation. And remember, if this is our characteristic equation, we can use partial fraction expansion to reduce it so that one of the terms will be something over s plus 1, and the other term will be something over s squared plus 2 squared. So if it turns out that that term results in a form that looks like s squared minus k squared, well, we're not in any more luck, because this is actually t cosine of kt. So that's no good. What about the inverse Laplace transform of just a constant over this form, s squared plus k squared squared? And it actually turns out that this is some sinusoid, but it's minus k times t times cosine of kt. So again, we have this t term here that is going to grow unbounded the longer that we run. So none of these are even marginally stable. Marginal stability means that if you have an input, that there are certain inputs that you have such that the system will not grow in an unbounded way. So that's no good. The reason that this is the case, again, is because we have repeated roots at the same point on the j omega axis. So just having roots on the j omega axis makes you so-called marginally stable or conditionally stable. Again, that means that there are some inputs for which you're stable, but that there could be other inputs for which you're unstable. And it's the fact that these roots are repeated, that is, the roots are at exactly the same place on the j omega axis, that makes you be unstable. So, how can we identify the difference between case 4 and case 3? Well, the first thing that we do is that we check the roots if we have numbers. So on an exam, you can always look with a calculator to see what the roots actually are for delta of s. And you'll do this anyway to confirm your answer and make sure that you have the right number of poles in the left or right hand plane. If you have variables, you can look for patterns such that you're going to get a factorization. And by the way, if you have variables, you may want to confirm that you're not going to get a row full of zeros if some variables happen to be 0 or equal to one another. So for example, you might end up substituting something like s prime for s squared, and you'll see that you'll get s prime squared plus 2s prime plus 1. This is the same as s prime plus 1 squared. So this is a good way to factor if you just have some kind of a variable. For 2 and 1, maybe 2 is b and 1 is a. You can make it look like this. If b is equal to 2 times a, then you're going to have a problem with repeated roots at the same point. So here we have 4 roots at plus or minus j1 when we have a transfer function, when we have a polynomial s squared plus 1 squared as part of our characteristic equation.